Good morning, everybody. And Robert, thank you very much for inviting me to Munich. I had not been here for a very long time, and frankly, when I arrived on Saturday at the Hauptbahnhof, of course, in a nice ICE train versus like 1985 when I came here for the first time, I came in a very old train. I kind of reminded me of the time at the time. It was basically the previous huge investment in technology. It was that time was Siemens technology. I was working at the University of Eindhoven. We were starting to build basically a software stack for conventional CMOS, synthesis, placement, routing. We were collaborating with Philips, who was collaborating with Siemens. Noord-Perlach was just being built. And I got to spend basically half a year here in 1985. I got to stay in the Oomstrasse. And I can say, yes, I was in a very small room, but it was no problem because the beer garden was like just a block away next to the English garden. And indeed, you're right. Yeah, we spent every night there, so it didn't matter that we only had like tiny room to sleep here. So let's fast forward. Right? So huge investment in semiconductor technology, which especially in the Western world lasted well into the 2000s. Then a huge focus actually shifted to software. I mean, hardware became kind of an unnecessary necessity. Software is the real thing. Huge investment boom in software companies. Most of the hardware investment, especially in semiconductors, moved very far east or west, depending on where you are, but at least to Taiwan and to Korea. Europe and US started to fall behind in the investment in core semiconductors. But interesting enough, in the last couple of years, I think we're starting to see complete reversal. I mean, the beginning of COVID and the supply chain problems in critical chips, the basically defense and other implications, but also basically more mundane stuff, right? I mean, right now, the amount of silicon that we need for AI chips is just unbelievable. I like this quote in the Wall Street Journal, correct? AI chips, it's like toilet paper during the pandemic. I mean, can't get enough of it. So I think what we are seeing is a healthy interest in many places, including here in Germany, in really reinvesting in core technology, in hardware and in software. But we also start to learn that basically traditional APC can only go so far. And I think you talked about a superb introduction to that. Right? I mean, there are certain problems. I mean, we're already seeing it like AI and machine learning. We are really hitting the boundaries of what we can deliver with hardcore classical computing. So what we're seeing, there are other areas, machine learning being in the middle here. We're certainly closer to where we simulate nature, where potential of quantum computing is huge. I mean, there's enormous problem spaces out there, which we can hardly touch upon with classical computing, and we need to look at new computing paradigms. And to do that, it requires the full stack. It does require hardware, it does require software, it does require a full HPC cloud, as you said here, the middleware, the cloud, to access it, to really make classic computing and quantum computing play well together and basically cover everything in between. Because I agree with you, usability is very important, right? I mean, if we need a quantum physicist to program a quantum computer, we're not going to go very far. So we need to at least lift it to a level where other people can write applications. Also, the hardware opportunities are expanding very, very rapidly. So to basically build a software stack, we need to understand enough of what the hardware can and cannot do, or can do better or can do worse, to really target our optimization stack and figure out how to map our problems in this space and make them run well on a quantum computer. So looking at IBM, right, what we're trying to really focus on is try to run quantum circuits faster on quantum hardware. We're trying to basically chart a path to develop quantum technology, both the hardware and the software, that allows us to run noise-free estimators of quantum circuits faster than can be done on quantum computing. And we're starting to get there's some really, really interesting signs of real applications that can be run. And we are working very much with many clients, many partners, many research institutes to figure out what are key applications that can take advantage of quantum computers, can take advantage of QPUs, and really move the state of the art forward. So, what do I want to do today in my talk? So I give you the 3 keywords ready to fill in, yeah? So you don't have to guess afterwards. No, but first I want to talk a little bit about IBM's hardware. Because writing compilers, writing software toolboxes without understanding some of the key hardware characteristics is not going to go very far. And we need hardware, we need software. Then I'll talk a little bit about some of the tools in the tools box, but probably not too much, because I think many of the other talks that follow me will talk a lot more about other tools to put in the toolbox. And then I would really like to kind of open the discussion on how we are putting these tools in the toolbox together. Right? Are these tool chains, these tool pipelines that we're building, are they actually the right architecture? I think what we learned, and I'll draw a little bit of an analogy, when building very complex software to currently basically create the billion transistor classic CMOS chips, is that pipelines don't work. Because we have very complex interacting objectives, and maybe we should look a little bit differently how we put some of this whole compile stack together. Okay, but before that, let me walk a little bit through IBM's hardware roadmap, then talk a little bit about some of the software toolbox, and then come back to how we put the whole toolbox together here. So key focus on how to make quantum computers and measure their performance. We focus very much on scale, so basically providing more working qubits. On quality, because how good are your qubits? Right? Unfortunately, we cannot build perfect qubits yet, but certainly the less errors, the better. We're trying to build circuits, computers that can run as long computations as possible, fitting within the coherence times before your whole computation apart. In both of them, quality is very important. And finally, speed, because we still need to run lots of circuits. It's probabilistic computation, so you need lots of circuits over and over again, different configurations. So the speed at which you can run these operations to get your final results is extremely important, right? And there the whole software stack, the classic software stack, working with the quantum software, working with the quantum hardware, all together is extremely important. So let's look a little bit at the scaling of the hardware here. So this is the roadmap that IBM kind of put out there. We started with some smaller 27 qubit chips. Currently have scaled it up to the Osprey chip, the 433 qubits. Are very close to getting over 1,000 qubits basically in a single chip together. Then beyond that, we would like to scale outside the chip. We're looking to basically put chips together, have them communicate with classic communication, have them communicate with quantum communication, put them together to build significantly larger systems. So how we were able to get, for example, to the Osprey chip here, which is the 433 qubit chip. So one of the key elements is basically take advantage of 3D integration. Right? So we can use through silicon vias or through qubit vias to basically build circuits of different layers. So therefore we can have one layer which has the qubits, other layers being used for the readout circuitry, and basically finally another layer that kind of wires it all together. So the advantage is that we can significantly reduce the noise and the coupling that happens between the qubits, and therefore, even for these somewhat larger chips, get significantly higher quality of qubits together. When you look at that, here you see some of the initial T1 measurements that came out of one of the chips here. And if you go to IBM's Quantum webpage, correct, you can see all metrics for all the 60 plus systems that we have. Correct? We publish every single of most parameters of the systems, very much like your telemetry, correct? But all the machines are monitored all the time. They're calibrated, yeah, every so often. Latest calibration results are being published. So they're a great kind of source of information to figure out, hey, how reliable can we actually build these systems right now? And also a very important input actually to the compilers, and because when we recalibrate some of these systems, you'll see that things walk, right? So not necessarily that your computation that ran on certain qubits 2 days ago actually will run similarly, yeah, with similar error rates 2 days from now, correct? So it requires recalibration, requires adjustment. So the other thing that you see here is that basically our connectivity map is fairly sparse, right? Yeah, most of the qubits have 2 neighbors or have 3 neighbors, and this is the lattice that we put them together. Yeah? So clearly there's a balance between providing a lot more connectivity, but therefore a lot more opportunity for crosstalk, a lot more opportunity for basically neighboring qubits to affect each other negatively, right? Versus, yeah, the ability to much easier compile a program on there because you have a lot more bits that you can entangle. Versus this more kind of sparse map, yeah, where it's much more tricky to actually take your algorithm, map it effectively to this connectivity infrastructure, and include a number of solve operations and make sure that actually the qubits can compute in the right configurations and move to the right places. So clearly one of the challenges for our compiler stack with these chips getting larger and larger is how to kind of map to these connectivity maps. So if you go beyond that, as I said, we are looking at basically putting multiple chips together using a kind of a classic communication bus. Yeah? So this requires basically your circuit, your algorithm to be partitioned. Yeah? And some of the computations need to basically map to the classical domain. And luckily we invented some technique, a whole collection of techniques called kind of circuit knitting toolbox, that allow you to basically then take the quantum information, bring it to the next chip, and basically react to the information that you see there in your computation, right? So, but it brings an interesting problem with it, is how are we going to basically partition our circuits? What are the really good boundaries to actually insert some of these circuit netting techniques, to map a larger algorithm onto multiple chips here? So this is basically using classic communication. We're also investigating, basically in the cross-build chip, is say, hey, can we take multiple chips and can we actually have them communicate in the quantum domain with each other? Yeah? And can we build basically a quantum link between 2 chips here? And the answer is probably yes, but it's probably less reliable than the quantum communication on the chip itself. So again, what we're going to get here is kind of different type of granularities. Right? We get more reliable connections on chip versus less reliable connections here. So what part of your computation, or basically when in your cycle, actually are you willing to basically cross a chip boundary or cross back? Or how do you actually cross, not too often? Or how do you do it at a part of the computation which is less critical, and even if there is some noise, you can actually sustain it or correct it or provide some extra error correction at that point. Right? So, and how are you going to write a compiler that actually inserts this at the right point and partitions the circuits at the right way? So I think the great thing is that we have a pretty challenging, a pretty interesting technology roadmap put out there, but it also brings enormous opportunities for software and software optimization to take full advantage of this. And going one step further, we are looking basically to couple multiple cryostats together and basically build a quantum communications link between different QPUs that are sitting in different cryostats. So we get different. So first we have a challenge. How do we distribute our algorithm between classic communication, quantum communication, and how do we distribute our algorithms so that some parts run in different cryostats? And what are the right boundaries and what are the techniques that we can use to, in the end, to basically fit a complete communication back together yeah, that allows a huge algorithm to actually run on this huge quantum system, yeah, that is spread out like this. So looking forward, yeah, we believe by basically putting all of these techniques together, yeah, we can have a clear roadmap to build like 4,000 plus qubit systems, yeah, in the next 2 to 3 years. And if you saw the announcement kind of from IBM earlier in the year, we are really challenging the community, like by the next 10 years, by 2033, can we put a 100,000 qubit system together? Yeah? And we believe actually there is a roadmap to do that with current technology, correct? It's super complicated, yeah? It's super challenging because each of these links, each of these chips will be challenged in their own domain to scale. But if you put them all together, we believe there is a path with known technology, yeah, to get to surprisingly large, yeah, quantum systems. And of course that delivers incredibly interesting, yeah, challenges for the software stack to be able to effectively use these. So I talked a little bit how we are scaling up our systems and believe we can provide large number of qubits. And the next question, of course, is how good are they? Are they good enough to actually do useful computations? And there also very, very substantial progress. Right here you see basically measurements, yeah, of the gate fidelity, basically the error rate, yeah, going down. Low error rate is good because it gives you high fidelity, yeah, over the last 10 years, pretty much, or this is the last 5 years. Yeah. And you see basically a significant, yeah, improvement in the gate fidelity. Yeah. So right now we get to 99.9%, so 0.001 errors, yeah, in some of our latest devices. Yeah. Again, these are not necessarily the largest device. It's not necessarily that the largest chip also has the lowest error rate. Yeah. But there are devices out there with a reasonable number of qubits on which we basically get to this level of fidelity. So tremendous progress, correct? And starts to be able to run very significant algorithms. At the same time, yeah, look at the coherence times. Yeah. They have gone up by at least 100,000 over the last decades. By a huge amount of kind of techniques, yeah, in the way we construct our qubits, the way, clear materials, innovations, basically, as I mentioned before, how we basically package them, the chips over multiple layers, huge amount of progress has been achieved. And we're starting to get here into the millisecond type of range here. And this basically allows currently people to run 100 plus qubit circuits over 60, 70 basically C0 cycle operations. Right? So that starts to be significant size computations that are currently being done on real hardware. First papers are starting to appear with people doing this. And looking forward, correct, these are some measurements on some of the coherence times of the latest qubits. Yeah, we see we can scale this up certainly by a factor of 1, 2, 3 again. Yeah, allowing you to triple the circuit depth probably pretty rapidly. Yeah, with the new machines that will be coming online in the very near future. And therefore also one of the challenges that IBM put out there, correct? Yeah, on hey, can we build like 100 by 100 type problems, correct? Problems of 100 qubits, 100 depth circuits that really address a very interesting problem. And we believe we will be able to run these on actual hardware very, very, very soon. So then kind of moving on to speed. And what determines actually the speed of a quantum algorithm? Of course, one is basically the inherent speed of the gates itself. Right? If you have fast gates, your computation goes faster. Then the entire control stack, right? How can you, with very high fidelity, basically control your qubits, read them out? And we have had a lot of investment basically in advancing our key electronics in the stack there. And then basically the whole Qiskit runtime, the open QASM infrastructure around this, which allows you to run many iterations of a particular circuit on whatever is the available hardware, quickly, repeatedly, yeah, partially in classic computing, partially in quantum computing, yeah, and them all together, yeah, have significantly improved, yeah, the throughput and the rate at which we can run some of our key quantum algorithms. Yeah, so some of the improvements in the hardware, yeah, one is basically, yeah, replacing all these, yeah, single gold cables that basically go through the cryostat with some more of the flex interconnect patterns. Because when you're getting to hundreds and thousands of qubits, it's extremely difficult to wire them all up individually. Yeah? So we were able to multiplex them in there. We see significantly decrease in wire density in there, becoming a lot cheaper, and actually also become more reliable kind of throughout the wiring stack. At the same time, a lot of investment in the control. Yeah? While originally we started basically with off-the-shelf racks of waveform generators, we moved it to FPGAs, to custom chips, and basically we're building our third generation of our quantum control, which basically allows us to control the 400 qubits of the current Osprey chips from a single rack there. Yeah. And yeah, one of the interesting things that the advanced control allows us is basically the ability to enable dynamic circuits. Right? So what that allows you actually to do classic computation, measurements, or controlling of some of your qubits in the middle of your quantum computation. So you can use this to reset some circuit, do some measurements, do some if then else calculations, and basically, yeah, have that affect the next phase of your quantum computing. So this kind of improvement in the control stack has made this possible and allows us to much more seamlessly move back and forth between the classic and the quantum domain here. But again, it brings interesting challenges, yeah, for the software, for the compiler stack. Okay? Because where do you insert some of these operations? Yeah? What is the good place in your algorithm to actually move back and forth? Yeah? Do the measurements, go back to the classical domain, yeah? And how do you kind of decompose your whole algorithm to ensure that you do these dynamic circuitry at the right places here? And furthermore, we are exploring basically moving to acquire CMOS qubit controllers so that we can actually take them from the rack that's outside and move them into the cryostat itself, and therefore have more advanced control, can control more qubits, and do it at significantly lower power than it currently takes kind of to control these qubits with a rack that's sitting on the side there. So to make these dynamic circuits possible, of course, a lot of work was done in the hardware, but also a significant amount of work was actually done in the software. Yeah? We need to be able to provide ability to reset and measure some of the qubits, and make sure that we could basically insert some of the key instructions at the right part in the compiler as well to take advantage of this. But of course, an interesting question is, where do we actually insert? Like if we have a circuit, how do we partition it? Where do we insert some of these measurements? What's the most effective way kind of to decompose our circuit and take advantage of these dynamic circuits and dynamic optimizations? Yeah, one way we can use it basically for error corrections, right? Because we can compare different parities with each other, and therefore try to correct for them using these measurements. We can basically map some of the computations to different constellations of qubits on your chip, kind of compare the results, and therefore get more reliable circuits out. Or we can basically use them to easily set or reset a certain qubits, and therefore kind of reduce your circuit depth when we are preparing states, for example. So lots of opportunities kind of to use dynamic circuits inside your circuitry. A lot of possibilities to actually insert them at the right place or not. And then finally, of course, a lot of attention is being paid to error mitigation. Currently, a lot of focus has been on kind of the error mitigation through zero noise extrapolation. The way this works is that, basically you can extend your computation a little bit by stretching the pulses. You can extend the computation, which then opens up your window for more noise, right? Because there's more time for noise to come in from your neighbors. Which is interesting, right? Because you said this is the best operating point with the smallest, narrowest pulses. But let's make it a little bit wider, and we get to this point. Of course, undesirable, but what you can actually do is then project backwards and say, hey, if we would be able to narrow the pulse, which we can't because then the computation doesn't work reliably anymore, we can probably measure the energy here, and we can probably measure the error rate here at this point, right, by kind of extrapolating down. And if you have a couple of points on the curve here, this works surprisingly well. But the question is, again, where in the circuits are you going to apply this? And all the techniques here, we can basically duplicate or triplicate circuits, add gates there to kind of average out there, and invert some of the noise before we kind of continue the computation going onward. Therefore, again, trying to mitigate the noise that propagates through the circuitry mid-circuit. So if you look at it, very interesting roadmap of hardware. A lot of opportunities to deal with different circuits techniques. And as I mentioned before, very complicated hardware stack, right? How are we going to take a big algorithm, partition it into the key parts of the circuits that need to go and run on the key pieces of the hardware, going to run on the key parts of the chips? And how are we going to then map each of these such that they're kind of run optimally or run with the least errors on each of these chips? And how do you take this huge problem and kind of break this down in subsequent steps that in the end we can actually get to the most optimal results? So let's talk a little bit about several of the tools that we have in our toolbox. But then most interestingly, I think I want to open a discussion at the end in how are we actually going to put these tools together, right? And are we doing this currently the right way, or should we look at something different? So let me very quickly breeze over a couple of the techniques here, mostly kind of to illustrate the type of tools that we have, kind of to then drive the discussion for the latter part of the talk here. So as I mentioned before, if we have basically distributed quantum computing, we have to cut some of our circuits at certain places and say, hey, we need to do basically circuit knitting, as we call it, and do basically quasi-probability simulation that allows us to take some of the quantum information and move it from one circuit basically to the other and continue the computations. So the question, of course, is where do you cut these circuits? In fact, you want to use that very minimally because it's extremely expensive to do this computation, but it can still be quite beneficial to mitigate a lot of noise that would otherwise accumulate in the circuit, or to basically cut larger circuits into smaller pieces that can actually fit on certain computers. So what can we use this circuit knitting for? One, obviously, is basically cut circuits. The circuit is too large, doesn't fit on your chip. You can cut it in multiple pieces and knit them back together. And you can also look at some core algorithms, which have huge amount of kind of entanglement in the core of the computation, less entanglement maybe in some of the preparation of some other stages, and say, hey, let's run one part on the QPU, on the quantum computer, where it's the most beneficial, and maybe some other part, despite that it's a little bit more expensive, run it on the cluster computer. And the two together can still give you complexity reduction and allow you to actually run larger algorithms on your QPU than you otherwise would be able to do. So a lot of opportunities to apply circuit knitting to actually take a big problem and cut it into pieces so it can be distributed among different chips. And then when we start to look inside each of the chips, we have lots of other opportunities. And I think there will be many other talks in the conference here to talk about how do we make sure that given the limited operations, given the coherence time that we need to fit it in, given the limited connectivity, we put in the right swap operations, we move the right qubit, the right logical qubits, the right physical qubits, try to find paths where we need to swap qubits that minimize kind of our error rates, and so on and so forth. Right? And then a lot of interesting papers, a lot of interesting kind of point algorithms that point out some of these key pieces. And you can these are just references to basically a paper that where this is all being summarized, where you can find these references back here. And that is a lot of interesting algorithms that people have come up, correct? It's a fruitful area for academic research, a lot of good papers. I think a little bit too much use of ILP, correct? Hey, if it looks like an ILP problem, just throw it in there and hopefully my solver solves it. I think there are maybe better ways to kind of take advantage of some of the problem structure. But a good amount of tools are actually being built in the toolbox here. But the big problem is there's a huge amount of dependency between each of these optimization steps. And it's extremely difficult to predict what one does to the other. So for example, a recent paper being referenced here basically looked at some of the different IBM pieces of hardware out there. So these are basically three machines here, our Eagle machine, the Hummingbird, the Peak Scale, and we show the C0 errors and the measurement errors, correct? And they vary quite a bit, over the different qubits in there. So the question was, hey, if you take your quantum circuit and you try to map it basically onto the most reliable kind of sub-circuit in your quantum computer, how much actually can you gain from that? So what the authors did basically said, hey, we just run the traditional compiler, map it to the kind of target computer that we have, which means that then we find all the kind of common subgraphs that are sitting in our circuit here. And we find basically a mapping to all the different places where we can map it on this particular piece of hardware. And then we're just going to score them. So we basically going to calculate, we take the error maps of our computers, which has particular qubits errors, the entanglement errors between each of these, and we compute basically a score for each of these sub-circuits being mapped to a particular piece of the chip here. And we do that for each and every one of them. And then we actually pick the sub-circuits, basically we pick the constellation of physical qubits that actually have the least error or have the, and map them to it. And surprisingly enough, you can see significant progress here. What's being plotted here is that for a set of benchmarks here, different number of qubits, we run the standard Qiskit compiler with optimization level 3. And then at the end, basically the post-processing is, hey, let's use this Mapomatic to basically redo our mapping and map them to basically the qubits that are the best. And how much can we then basically improve the fidelity of our circuit, and how much can we kind of recover? And you see where it's darker purple, significant amount of error could be recovered and fidelity could be improved here. So using the right qubits, extremely important. But when do you apply this in the system? Because potentially it takes extra swaps to get to the right. If you have a larger computation, it takes a bunch of swaps to maybe get to the right computations that sit in different places of your chip. If you can get there very reliably, it's great, right? Because you can plot a reliable path, you don't lose a lot of time, and your computation does not get derated too much. However, if you lose a lot, it's not worth getting to the other place. Yeah? So how do you make these type of trade-offs? So another interesting experiment I did said, hey, you know what? Let's take some different, basically this is the one where basically they minimize the number of CNOTs used for swaps. And here, let's add a few more different swap operations here. And sometimes the right places, sometimes the wrong places. Yeah? And you see it significantly degrades the results here. Yeah? So it shows kind of the interaction between how many times do I want to swap operations and make my computation longer to get to the right set of qubits to operate on, versus do I rather have my computation as short as possible but run them on less reliable qubits. And this is only kind of for one sub-circuit that you want to run most reliably on part of your quantum computer. Another paper basically goes one step further and says, you know what, if we have a larger algorithm, can we cut it into multiple places? So basically, take my circuit, cut it into a bunch of sub-circuits, given a particular maximum allowable cut size. And for all these configurations, let's just do the mapping. You just use the Map-O-Matic from the previous paper and just map them and compute all these scores. And then the question is, are we going to run this piece of computation on one particular hardware and one particular piece of hardware? Or if we say, hey, we have enough execution time, we can just actually stage them and run them after each other on the same piece of hardware. And how does that affect our results? And by placing these sub-circuits correctly on different pieces of hardware, how much can we actually gain? And again, surprisingly large amount here. If you look for these particular circuits, basically the kind of baseline reliability, fidelity here is shown on the left here. Then if we do kind of measurement error mitigation, one of the measurement error mitigation techniques that I showed on the previous charts, you get some step up here. But surprisingly, basically by cutting the circuit and placing it on some of the best hardware for the particular circuit, we get a significant step up even beyond what is possible with the measurement error mitigation. And if we apply mitigation on top of that, we see scores even going higher. And then the authors kind of extended this to basically run this on larger qubit circuits like 10 and 20, and the results are significantly more pronounced. Like the overall fidelity goes down, but the results are significantly more pronounced. So the net of all of this is that there's a huge amount of dependency of all these operations, of all the optimizations that we can do in the tool chain. So the real question that I have here, is it still the right idea to use a pipeline? Because on one side we have the effect that many of the decisions that you make earlier on affect decisions later on. Decisions later on might undo what you assumed before. And we don't have enough reliable estimators to actually guide us through the process and make the right decisions at every point throughout the process. So interestingly, this made me kind of think back to the mid-90s. When I was working on basically a tool chain for traditional CMOS. We had high-level synthesis, we had logic synthesis, we had placement and routing. We nicely staged it out. We tried to predict from early on what happened later on, and tried to build really good chips. And this actually worked pretty well till the mid-90s. This is actually a chart I just pulled out of an old deck from the mid-90s. And then it started to fall apart. And why was that? Because the predictability went out the door. Because originally, gate delay was basically dominating anything in the circuit. So you could, during synthesis, you could predict how long it took for a circuit to run by just counting the levels of gates. There was no crosstalk from wires, there was no delay from wires. So this tool chain from left to right worked perfectly well. Unfortunately, wires became dominant in the next range of technologies. So the gate delay is only a very small fraction. Most of the delay goes into the wires. Variability of the wires is huge, so it's very difficult to predict how long it actually takes a signal to get through a wire. And on top of that, wires are very susceptible to crosstalk. Right? Depending on who is above you, below you, next to you, left and right, you suddenly get a lot of noise injected into your computation. The good news was that in the digital domain, we had 15 years to gradually get used to this. It just got worse. Every technology knows every 2 years it got a little bit worse. And said, we were scratching our heads and says, okay, we have a problem here. Right? So, predicting became gradually more difficult. Design decisions interact. And the system became more difficult to control. Like this is a drawing from one of my colleagues. He said, hey, you're trying to sit at the beginning here and pull this level, try to predict what's here, and then go back to the beginning and try to iterate. But even when you iterate, you don't really know what the decisions have down the road. So it became a kind of unmanageable process. But as I said, the advantage that we had about 15 to 20 years kind of to gradually get used to this and transform our tool chain into something different. Unfortunately, with quantum computing, we're actually starting on the other side. We start with a pretty unreliable computation to begin with, where many things affect each other right from the start. And maybe we are focused too much on building tool chains from left to right. So what did we do in the digital domain kind of to overcome this? We basically said, hey, we need to build tools differently. Instead of having a linear tool chain, we need basically, and I'll actually jump right away to the right. We need two collections of tools. One on the top here deals with the big partitioning problem. Correct? If you have a billion transistor circuit, how are you going to partition it into huge chunks that can be floor plans? Right? You have the different accelerators, you have the different GPUs, you have different CPUs. Below that you have significant units. Right? So this big partitioning needs to be guided by some high-level estimates of timing, of power, of noise. But the accuracy of these estimations can be pretty cruel, right? Because you make very high-level decisions. And then at the bottom, when you start to kind of take each of these blocks, which are 1, 2, 3, 4, 5 million gates, and you start to map them to the individual gates, individual wires, individual routes on the chip, you need extremely detailed information. Right? You need detailed information on what it does to timing, what it does to noise when you run two wires next to each other, what it does to the power, to accurately predict when you create certain configurations, on what effects it will have, basically, and take the right optimization decisions. And in addition, the optimization tools, the synthesis, the placement, the routing of the circuits, they don't happen as a pipeline. They happen iteratively, constantly. You synthesize a little part of the circuit, you place them, you route them, you do it again, you undo it. You basically ask these analysis tools to give you the information, and you do and undo again and again and again. And it becomes kind of a big converging process that in the end leads to an acceptable result. Acceptable, which means it fits in the area, it fits in the time that you want to do your computation, and your circuit actually runs. So this relies on very good estimation tools, correct? Can we estimate the timing of our circuits? Can we estimate the noise and the crosstalk? So can we build basically a set of estimators for each of these that affect our quantum hardware? It requires these estimators actually to be able to run preferably in an incremental fashion, which means like I have a network, I swap a few gates, and it can tell me if it likely gets better or worse. You don't want it to then completely go off and rerun its estimation, because that's going to take forever. So being able to do this incrementally and basically tell you, am I walking in the right direction, is extremely important for the estimation tools. And these optimization tools, they need to run in small pieces. Not like, hey, let's place every qubit, let's place the entire circuit, or let's route everything. No, you need to be able to run in partitions of the design, piece by piece, and provide additional granularity, detailed information to do this. And a very important piece in the middle is basically have a data model that connects all these pieces together. Right? So the data model is a continuous reflection of the state of the world, which gradually gets more and more refined, which the estimation tools can look at and provide really good estimates, and which the optimization tools can gradually refine and make better. Again, very different than, I think, the compiler mindset, which is really from stage to stage to stage, and what has happened, and I move on to the next piece. So I think one of the things that might be interesting to look at, for example, is, there's an open database, right? Open access, which is a chip-level database. I'm not saying this is immediately applicable to a quantum computation, but it has some really interesting concepts, right? It supports hierarchy incredibly well. It has a concept of occurrence hierarchy, which means if you take a circuit, the same circuit, but you put it in different places, it can behave differently. Okay? So the occurrence, where it appears, might behave differently depending on what's around it. So to be able to natively represent it in your database and therefore have different analysis results for different occurrences of the same thing is extremely important to make trade-offs. There's a concept of observers, basically, which says, hey, something in the network changed, so analysis tools go and redo your analysis to give me the information back to change here. So I think there's a lot of interesting concepts, that maybe we should think and say, hey, should they become part of the way we actually are going to construct quantum toolboxes as well? You can go to the SI2 webpage, there's a huge amount of documentation, but say, hey, the most important one, there's some key concepts, I think, to look at. And the time is right, because when we look, we're starting to get to utility scale type of experiments. This is just a collection of very recent papers, where people are starting to run 100 plus qubits, thousands of gates, as I said, 60, 70 circuit level depth, and we expect this to explode or to grow very, very rapidly with some of the distributed quantum computers coming online very, very rapidly. So the need for more advanced, smarter, compiled optimization stack is absolutely there, and I think there's a lot of interesting ideas out here. So from IBM, we are working hard to basically make quantum utility real. And I have seen some interesting experiments. Right? There was some interesting demonstration where we ran on a huge HPC cluster at Lawrence Livermore, ran similar algorithms, tried to compete with the quantum computer back and forth, and saw some nice utility about the kind of speed that we got about the quantum computer. And we are continuing to basically build out our fleet of quantum computers throughout the globe, and basically hook them up into many multiple cloud regions so that you actually can combine all these quantum computers together for potentially very large, useful computations. These are some of the machines that are online, different locations. Big data center is in Poughkeepsie, New York, where I have my office. A lot of the more experimental machines are in Yorktown, which is a little bit close to New York City. And many others kind of spread around the world. There's a data center being built here in Germany, in Eningen, close to Stuttgart, which will house our European multi-cloud region next year, as well as machines in Korea and Japan here. So I think we are working hard to provide a significant amount of hardware that's accessible to very many people. Yeah, if you go to IBM's Quantum web pages, you see accessibility through many different plans. Yeah, from a few shots, individual plans that everybody can use. Yeah, to very elaborate collaborations that we have set up with key universities and key industries around the globe. I think we believe we are on the brink of really starting to apply quantum computation to interesting chemistry problems. People have been studying like corrosion, battery chemistry, and basically seeing very interesting results, right? Maybe results that they can just apply on a conventional classic machine again, but they would never have done this if they wouldn't have seen the quantum result in the first place, right? So there is a nice horse race going on in kind of developing quantum algorithms, see how they run on quantum hardware and learning from that. And we believe we are pretty much on a pretty steep curve to quickly propel out of that and make quantum utility useful to very large scientific communities across the globe. And with that, let me open it up for questions here. I think we have a few minutes left, and thank you.